Alright guys, I'm back and we're going to talk some more about some OpAmp stuff. I'm going to do this video where I'm just going to kind of do a brief review of OpAmps so it's fresh in your head, and that way hopefully anything that I might have missed you'll remember. So everybody remembers hopefully that I drew an OpAmp. This is typically what the symbol looks like. You're going to have a positive and negative, and then you'll have a VS on the positive side and a VS on the negative side. You'll have an output. We'll say that's V out. We'll call the input V plus and V minus. So it's very similar to a differential amplifier. And you can also, most people don't draw it, but you can also say there's a ground. So typically an op-amp has 1, 2, 3, 4, 5, 6 ports to it. And so you can look at some chips and you'll basically see that. Some of the uses for op-amps, you could say that, well, the thing that we've been studying in this class is amplifiers. So whatever amplification. And that's probably what we're mostly going to focus on. But they're also used as filters. We call them active filters. And they have active components in them versus a normal filter has only passive components like capacitors and inductors and so forth in it. And then there's also this whole thing of analog computers. That's a whole field by itself too. So op-amps are used in those too. Mostly what we're going to focus on in this class is amplifiers and a little bit of filtering. So the first op-amp that we're going to talk about is just a basic unity gain operational amplifier. But before we get into that, I'm just going to review one more thing, and let's look at what an op-amp basically looks like if we broke it into a circuit. So you have two input terminals, right? And we'll say this is Vn, and we'll say this is V plus and V minus. That's pretty similar to the differential amplifiers we've been studying. And then we can say this resistance right here is Rn. And you can kind of, let's just draw the whole op-amp picture in here. And then you could say there's a dependent source in here. And we can say this guy is going to be A, V input. So whatever is on the V input between those two V plus and V minus terminals are going to be amplified by the number A. So if A is 1,000, then it'll be 1,000 and so forth. Alright, and then we have our V out. Alright, something else to remember, if we look at an op-amp and we look at the input-output terminals, we're going to say there's some current I plus and some current I minus going in here into these input terminals. Now ideally what we want is we want I plus to be equal to I minus, which is 0. So we want I plus and I minus to be equal to 0. Also, when we look at our V plus, the difference between V plus and V minus should also be equal to 0. So it's very important for you to keep these two things in mind if you want to understand op-amps and kind of what their ideal behavior is. Now typically we'll say, like for example Rn, we want it ideally to be equal to infinity. In reality, you can get them anywhere from 10 mega ohms to I think 1 tera ohm is what I read. So very high input impedance on op-amps. And obviously if there's a very high input impedance, then you can see why I plus and I minus are going to be equal to 0, because there's going to be virtually no current flowing into those input terminals. Cool? Alright, so next thing we're going to talk about is a buffer circuit, unity gain. I think I mentioned this before to you guys. So I'm just going to draw it out. It's going to look something like this. And we're going to have our output, VO, and then we're going to have input coming into it, and we'll call this VN. And now, in order to get unity gain, what does unity gain mean? Unity gain. What that means is we're saying that VN is going to be equal to Vout. Now if we go back up to this little diagram right there, you'll see that Vout, or maybe I should just go VO to keep everything consistent, is going to be equal to A VN. So then for A VN to be equal to A Vout, A has to be equal to 1. So we want to design this circuit so it's 1. And the way we accomplish this is by looping the circuit back. So we're creating a feedback loop that basically tells the output input to match up. And that's just by, let me draw this a little better. That's just by connecting the output back into the negative terminal of the input. Okay, so when we do this, then we're going to get A is equal to 1, and it has some really cool implications. So let's look at a little bit of them. So before I actually really go into it, let me give you some motivation for why this is important. So imagine you had a voltage source, and it had some input RS, and let's call this VS, and we'll just say this guy, let's say it's 10 volts right here. And I'm going to draw a little cloud over the whole thing so that you can kind of see that this is my input. Alright, so now I want to feed this into a next stage of whatever electrical circuit I'm designing. Imagine this just being like a Thevenin equivalent circuit that's feeding into this next stage. So we got another stage right here. Let's make this cloud red. Alright, and in this stage we have some output that we want to measure, and we also have some resistance, and we'll call this guy RL. And just to give some meat with the potatoes, let's make RL 1 kilo ohm, and we'll say RS is 99 kilo ohms. If I can make a K, that would really help. Okay, and we'll say this is Vout relative to our ground here. Okay, so this is just a normal circuit. We don't have any active components in there. We have some stage, some input stage right here. Let me take this Thevenin out and write input. We got some input stage right here. We got some output stage right here. Okay. Now, you can kind of break this down pretty easily and pretty quickly because you've all had circuit analysis and you should be able to do this, but you can say, well, Vout is going to be equal to Vs, and then there's a voltage divider involved, and so we're going to say that it's going to be RL times the sum of all the resistances in the circuit. So that's going to be RS plus RL. And so if we actually find a number for this, it's going to end up being 10 volts times RL, which we said is 1 kilo ohm. and divided that by the sum of all the impedances. So we're going to have 99 kilo ohms plus 1 kilo ohm. And then if you simplify that, you should get 0.1 volts, if I'm not mistaken. Yeah, 1 divided by 99 plus 1, that's 1 over 100. 1 over 100 times 10 is going to equal 0.1 volts. So you can see that if our stage here at V out expected, say 5 volts, say like a basic voltage that your system is using throughout, your impedances in these two systems just caused your voltage to drop all the way to 0.1 volts. And you can it kind of makes sense, because with the power has to be the same. So the current that's going to flow through here, and it's going to go in here, is going to basically create a scenario where your voltage, wherever it's going onwards, is going to be affected by the current going down through your load resistance there. And so we want to create something basically that says we want to keep voltage constant and adjust the circuit so that whatever those impedances are going to affect it. Now, you know Ohm's law is V equals IR. And if you want to keep V stable, and R is going to change from your circuit, then I has to be a change to keep V constant. So say your R, your impedance drops, then your current has to go up. And that's typically what you see in a unity gain amplifier. Really what it is it's a current amplifier. So you can think of it as a current amplifier, or a current source in a sense. Because by keeping, if you want to keep VO exactly the same as VS, if these impedances change, then there has to be more current flowing through it. So it's a really cool thing, because between two stages of your whatever your circuit is, you can basically boost up the power in it, because you're boosting up the current, keeping the voltage equal. All right. So you see the problem is just connecting these two together. So let's take a look at how we can do this with a unity gain amplifier to get past this. And I'm sure you can already guess, because it's pretty simple. So you have your unity gain amplifier, and we said that we had some. Let me see if there's a magic way I can copy and paste this again. We have this input stage. I'm just going to copy it and paste it down here. Uh-oh, I might need to scooch all the way down the page here. Alright, so you got your input here, and now we're not going to connect these two stages together by themselves. We're going to add this unity gain buffer in here. Okay, and then we're going to connect on our next stage, which was a load resistance, RL, and we said this was 99. No, we said this was 1 kilo ohm. 1 kilo ohm. And then the left side was 99. Alright, so what happens now? Well, like I said, if this is our VS right here, we're going to end up having VS at its output too. When you look into this terminal, you're basically going to see no current flowing in it. So we're just going to kind of measure between these two ports, right? We're going to measure and see, okay, well, there's VS between these two ports. And then this OpAmp is basically, because it has a gain of 1, it's going to basically say, okay, well, there has to be VS there. So it's actually going to be pumping a lot of current into, my goodness, I'm always doing this. It's going to pump a lot of current in here to match this circuit being VS and then this being V out. And so if you have this, because there's VS over here in this output junction of the unity gain buffer, you're going to have VS over there. and this Vs right here is relative to our ground right here, and so that means that our V out is going to be Vs again. So it's a really useful trick, basically just adding in this unity gain buffer, and then it matches our impedance. And if I have time, I'm going to show you another really cool example that is used when you connect coaxial cables, like video cables, the old school, or like a cable TV cable to a TV. There's a really cool op-amp circuit that they build to basically match your input and output to be 75 ohms, which is typically what those types of coaxial cables impedance are on. Cool. So let's see, is there anything else I need to cover about unity gain buffers? I don't think so. Basically, like I said, don't forget that buffers, they boost power. Let me just write this in here in the slides. Without changing the output voltage waveform. All right, I will see you in the next video.